Every power plant has an optimum operating temperature to make best use of its power. We humans function best at 98.6 degrees Fahrenheit. Raise that temperature a degree or two, and performance falls off rapidly. So power plants need some sort of a cooling system. There's air cooling, and there's liquid cooling, which normally uses water as the major coolant source. Engines have the same problems with heat. Of the total fuel an engine burns to produce power, only about 1/3 of the heat can actually be used for power. What happens to the other 2/3 of the heat engines produce? About 1/3 goes out the exhaust, but the other 1/3 must be removed by the engine's cooling system if it's to operate properly. So the cooling system is an extremely important part of the engine. Kept clean and in good repair, it helps keep the engine operating at the proper temperature. The basic components of the cooling system are the radiator, pressure cap, the fan which draws air through the radiator, the water pump, coolant passages within the engine, the thermostat, and connecting hoses and pipes. Each of these components is designed to match the job it must perform. Together, they work as a balanced team to control and circulate the final basic component, the coolant, through the engine. The coolant and the cooling system are interrelated. The coolant must help maintain the cooling system components if the system is to accomplish its vital job of regulating engine temperature. At full load operation, flame temperatures in the engine's combustion chamber can go as high as 3,000 degrees Fahrenheit. The piston, liner, head gasket, valves, and injector, which are directly exposed to the heat of the combustion, would melt if it weren't for the cooling system. Heat is generated in the engine from the burning of fuel and from the continuous friction of the many fast-moving and close-fitting parts. The coolant circulates around and past high-temperature areas through passages in the engine. The heat is conducted through metal to the coolant, which flows to the radiator. There, the heat is dissipated to the air. So the cooling cycle is fire to metal to coolant to air. Simple enough, but very costly if the system and the coolant are not properly maintained. Let's review this in more detail. Rust occurs in the engine when water comes into contact with cast iron. While a good rust inhibitor will not rid an engine of existing rust, it will prevent rust in a new engine. Quality ethylene glycol antifreeze contains rust inhibitors in sufficient quantity to do the job. Mineral deposits occur when water with any mineral content comes in contact with hot metal. Water boiled in a tea kettle is a good example of this chemical reaction. This scale or deposit builds up on the metal and creates an insulation barrier that prevents heat from moving rapidly through the metal into the coolant. In fact, 1/48 of an inch of mineral buildup equals the same insulation characteristics as an additional inch of cast iron. The buildup on this liner equals 1.5 inches of cast iron. Chlorates prevent these mineral deposits. A good rust inhibitor contains sufficient chlorate to stop mineral buildup. Mineral deposits and rust damage the engine. Typically, they coat metal parts and cause hot spots. They wear out water pump bearings and seals and cause piston, ring, and liner failure, as well as failure of gaskets and packings. Mineral deposits and rust clog the oil cooler and radiator, and they reduce cooling efficiency significantly. Another culprit that causes clogging is oil and grease. This comes from leaking gaskets, poor servicing techniques, and pouring water into the radiator from an oily container. Remember that oil breaks down anti-rust and anti-mineral additives in the coolant. Water becomes acidic whenever metal dissolves in it. Seepage of head gaskets allows combustion gases to enter the coolant and increase its acidity. The acid then attacks all metal and rubber parts of the cooling system. If allowed to go unchecked, this chemical process accelerates and becomes a vicious cycle. Again, A good rust inhibitor will neutralize acid. The best insurance against rust, mineral deposits, and acid is an annual program of preventive maintenance of the cooling system. As we've mentioned before, rust inhibitors only keep the rust from forming. They don't get rid of it once it's in the system. So once a year, drain out and discard the old coolant. If the coolant drained out was rusty, use a good flushing agent to rid the system of rust. The system should be thoroughly flushed clean. In extremely stubborn cases, you may need to remove the radiator for chemical or mechanical cleaning. Now fill the radiator with clean, mineral-free water and antifreeze or a reputable rust inhibitor. If you have hard water in your area, purchase soft water for the system. It's relatively inexpensive, far less costly than the damage hard water can do. Never add water to a radiator that has been taken from a drainage ditch, irrigation canal, or similar source. Sediment from the water settles around the lower portion of coolant passages in the block. This prevents heat transfer from hot areas, such as the cylinder, and can result in costly repair. Use a good brand of ethylene glycol-based antifreeze. This is permanent antifreeze, which simply means that it won't boil away, not that it lasts forever. Add compatible inhibitors if necessary, but remember, most good antifreezes already contain them. Once the system is filled, it's essential to maintain coolant level high enough to prevent air from entering the system. Air is a good insulator, so it retards cooling. And since it contains oxygen, it accelerates rusting and corrosion. With the high volume of coolant flowing through the engine, small air bubbles want to stay entrapped in the system. Special baffling in the radiator top tank removes the bubbles from the system, and this is called de-aeration. Without sufficient water above the baffles, they cannot do their job. Coolant flows through the system with velocities high enough to give good heat transfer and with capacity high enough to carry the heat away, depending on radiator and water pump size. Coolant flows between 1/2 and 3/4 gallon per minute per 1 horsepower at the engine flywheel. Therefore, an engine with 100 flywheel horsepower might have a total coolant flow of about 65 gallons per minute during full load operation. Maintaining the coolant assures the maximum life of all components of the cooling system. It's the one thing all these components have in common. But now, let's discuss the components in more detail. The radiator is where the coolant releases heat to the atmosphere. For the radiator to do its job properly, it must be kept clean, inside and out. The pressure cap has two functions. It allows pressurization of the system to raise the boiling point of the coolant. And it allows air to enter the system after engine shutdown. Each 1 pound of pressure per square inch will raise the boiling point of pure water 3 degrees Fahrenheit. So, as an example, a 7 psi radiator cap increases the water's boiling point by 21 degrees. Thus, a 7 psi radiator cap will raise the boiling point to 233 degrees at sea level. As the altitude increases, the boiling point is reduced. The pressure cap must be of correct specification for the system, and it must seal where it contacts the neck of the radiator to allow pressure buildup and prevent loss of coolant from the system. To check the radiator cap for correct opening pressure, use this special radiator cap tester. The fan's size, design, and RPM determine the volume of air moving through the radiator to remove heat. The fan depends on fan belt tension to maintain its optimum speed. The water pump is required to circulate many gallons of water through the engine and radiator every minute. In the case of belt-driven pumps, the belt must be correctly tensioned to assure peak efficiency. Connecting hoses should be checked periodically since they deteriorate with age. Usually the failure occurs inside the hose where it can't be seen. Even though a soft hose might appear normal on the outside, it may look like this on the inside. If it does, it will eventually collapse and restrict water flow at high water pump speed. Many engines are equipped with a crankcase oil cooler, which is a radiator-like core enclosed in a housing. Oil flows through one portion of the core, and coolant flows through another. This compounds the job of the cooling system, but fortunately, it's designed to handle this additional load. Many modern high-performance engines are equipped with turbochargers, and, for even more power, turbochargers with intercoolers. Oil that flows through the hot turbocharger must be cooled in the oil cooler. Since a turbocharged engine burns more fuel, there's more heat to be removed by the coolant. An intercooler is a radiator-like unit located in the intake manifold. Coolant circulates through its core and removes heat from the intake air that has been heated by the compression of the turbocharger. The result is still more work to be accomplished by the cooling system. As you would expect, it is designed accordingly. The thermostat is a heat-operated valve which controls coolant flow to maintain the correct engine operating temperature. During engine warm-up, the thermostat remains closed. This allows coolant to continually recirculate through the engine cooling passages without passing through the radiator. So, the engine warms up faster. During light engine load operation, the thermostat partially closes to prevent subnormal operating temperatures. This word of warning: never allow an engine to operate without its thermostat installed. Most engines have a normal operating temperature of at least 180 degrees Fahrenheit. When an engine runs below best operating temperature, fuel that hits the relatively cold combustion chamber or cylinder walls will not burn. This raw fuel dilutes the lube oil on cylinder walls and helps carry contaminants into the crankcase oil. This excess fuel also reduces the oil film thickness on the walls, which in turn allows faster wear of rings and liners and increased blow-by. This contamination results in stuck piston rings. Cold engine operation results in condensation in the crankcase, forming sludge in the oil, eventually resulting in failure of lubricated parts. This is especially true of pistons and crankshaft bearings. A properly functioning cooling system performs the critical task of removing heat from the engine. In turn, a properly conditioned coolant is the best way to maintain cooling system components for long, trouble-free life. Modern high-horsepower engines require more cooling power than ever. Proper preventive maintenance of the cooling system will contribute to top machine performance, everyone's goal. Efficient cooling systems that engines may live.